Okay, so for the second talk of the day, please welcome Sam Nelson from Claremont McKenna College. We're very glad to have you here today, and the seminar will be about Quandle cohomology, Quiver representations. Please, here is your talk.
All right, great, thanks. Yeah, it's great to be here at the first International Online Knot Theory Congress. Um, excuse me. So, yeah, I'm Sam Nelson from Claremont McKenna College. First, since this is in honor of the 80th birthday of Lou Kaufman, let me just share a little of my history with Lou. I first met Lou back when I was a grad student at LSU. It's Louisiana State University in Baton Rouge, Louisiana. Lou came to a conference in Louisiana, and at that time I was trying to decide between a few different project ideas for my dissertation. As a very scared, nervous, terrified grad student, I went up to Lou with my list of possible ideas and asked him for his advice about which of these different ideas about virtual knots would he recommend that I pursue. And he gave me some very helpful advice and was very friendly and made me feel at ease. Then several years later, I was at a conference in Texas, Texas Tech. During lunch, Lou and I were just talking with each other, having some conversation, I think about proofs of the Pythagorean theorem, when another grad student came up, also very terrified and with a list of things to ask Lou about. And I was like, yes, the cycle has completed. So, all right. So let me acknowledge partial support from Simon's Foundation. And let's go ahead and get started. Let me also just drop a bit of shameless self-promotion here. I have a music project that I call Modulo Torsion, where I release industrial dance music composed from colorings of knots, from Homset elements of knots by Quandles, biquandles, tribrackets, and other algebraic structures. If you're interested, you should check out my Bandcamp or my YouTube site here. Okay, so this is joint work with actually no one. This is a rare solo paper and my 100th paper on archive. Okay, so to mathematics. We're going to do a lot of review before we get to the new material. So first, quandles. What is a quandle? So a quandle is a set X with a binary operation triangle satisfying these three axioms. So it should be self-distributive, should be right invertible, and every element should be idempotent under the quandle operation. I've noticed that some authors also include a requirement for a quandle to be non-empty, but there's not really any reason that a quandle needs to be non-empty. I mean, the empty set satisfies all three of these axioms perfectly well. So I personally consider the empty set to be a quandle. Excuse me. Okay, so some standard examples, some non-empty examples of quandles include the conjugation quandle of a group, or more generally, the n-fold conjugation quandle of a group, where you can conjugate x by y n times for any integer n. If n is 0, then this is the trivial quandle. If n is 1 or -1, depending on your convention, then this is the sort of standard conjugation quandle, but you can do this any integer number of times. There's the core quandle of a group, which is also a group as a set, but then with the quandle operation given by y, x inverse y. This is, if you look at the conjugation, this is kind of subtly different. It's like moving the -1 from the y over to the x. Okay, and then Alexander quandles are quotients of the ring of Laurent polynomials in one variable by some ideal. And this is a quandle with quandle operation t times x t times x plus 1 minus ty is our x triangle y. Okay. So another very important example of a quandle is the knot quandle. So every oriented knot or link, and this includes virtual knots as well and virtual links, has a knot quandle that's defined from any diagram of your knot or link by a presentation with generators corresponding to arcs and relations corresponding to crossings. So in 1980, David Joyce proved that the knot quandle determines the group system, so the knot group and the peripheral subgroup. And so hence is a complete invariant of knots up to ambient homeomorphism. So this is part of my interest in quandles and part of my sort of,
Well,
yes?
don't forget about Matveev and who proved it.
Yes.
Yes.
Yes, that's right. Thanks. Yeah. So at the same time, yeah, Sergei Medvedev also obtained the same result. Yes, independently. Thanks. Right. So for me, this is kind of part of my philosophy of studying knot theory is that, I mean, the knot quandle contains essentially all of the information about the knot. And so in some sense, every other knot invariant should be obtainable from the knot quandle. In some sense, I mean, this is only for invariants up to ambient homeomorphism. If you are interested in ambient isotopy, which I am also, then there is still more to be done. Okay, so one of the things with the knot quandle, let me go back here. One of the things with studying knots by studying knot quandles is that when you have a presentation, when you have an object given by presentation, determining whether two objects that are given by presentations are isomorphic comes down to finding a sequence of tsetse moves changing one presentation into the other. And with knots, generally with knot quandles, for me anyway, the easiest way to do that is actually just to go back to the knot diagrams and find a sequence of Breidemeister moves. So if we're trying to get invariants that are more sort of computable, just looking at the knot quandle itself is kind of difficult. So one way to use the knot quandle to define computable knot and link invariants is to choose a finite quandle X and then consider the Hom set. So what is the Hom set? It's the set of, well, we can represent it as the set of quandle colorings of a diagram of the knot. So for a finite quandle X, excuse me, for a finite quandle X, an X coloring of an oriented classical or virtual knot diagram looks like this locally. So we're attaching elements of X to each of the arcs in the diagram. And then when X goes under Y, if you orient Y pointing down, when X goes under Y from left to right, it becomes this Z, which Z here is X triangle Y. If we have a virtual crossing, then these colors don't change when they go through the virtual crossing. Right, and so given a finite quandle and a knot diagram, you can just try assigning all of the possible assignments of quandle elements to the arcs, and then the ones that satisfy the coloring condition at every crossing are representing Hom set elements, and the ones that don't don't. Okay, so let me show you an example. So if we take our set X to be 1, 2, 3, 4, you can verify by just doing just exhaustively checking that this table defines a quandle structure. So here, like 2 triangle 3 is 4, right? And now let's consider the 4, 2 torus link. If you try all of the assignments of numbers 1, 2, 3, 4 to the arcs in the diagram, and you check which ones satisfy the Quandle coloring condition at each crossing. You'll find that there's a total of 16 colorings, and so they look like this. Right? So this list of 16 X-colored diagrams is a way to represent the Quandle Hom set. So it's sometimes been incorrectly stated in the literature that the Hom set is not an invariant, only that its cardinality is. And that's not true. The Hom set itself as an abstract, as a set of homomorphisms, is for sure an invariant. But what is true is that how we represent it depends on our choice of knot diagram, right? So like back here, if we were to take this diagram and do some Reidemeister move, then that's going to give us a different representative for the same Hom set element, for the same. So what is really a Hom set element? It's a Quandle homomorphism from the knot Quandle to our finite Quandle X. Okay? So this is analogous to the situation in linear algebra, where if you choose a different basis for your vector space, then it's going to give you a different matrix representing the same linear transformation. And so in this situation, I like to think of the Reidemeister move, the Quandle colored Reidemeister moves, right, as playing the role of the change of basis matrix, right? So just to be clear, if we come back here and we choose one of these Hom set elements, and you do a Reidemeister move, that's going to bring the colors with it, right? Like if you do a Reidemeister 1 here on this strand, I don't know if you can see where I'm pointing. If you do a Reidemeister 1 on this strand, then the new strand is still going to be colored too. Okay. All right. So most of my research involves what I call enhancements, right? The easiest computable invariant from the Hom set is just the number of elements in the Hom set. So that's called the Quandle counting invariant. It's a nice integer valued invariant of knots. And I mean, for a given Quandle, it's not, I mean, it's for sure not a complete invariant. But what might be true is that for any two knots that are different, it may be the case. I think it's still conjecture, but that there exists some finite Quandle such that the counting invariant distinguishes the two knots. But in any case, so maybe the point there is that don't get too hung up on any one particular Quandle. Really, we want to think about the set of all Quandles overall. Okay, so then anyway, if you find an invariant phi of Quandle colored knots, so in other words, an invariant of knots that depends on the Quandle colors, but that doesn't change when you do Quandle colored Reidemeister moves, then such a phi defines what I call an enhancement, which is a stronger invariant that on the one hand determines the counting invariant by taking the cardinality of the multiset of phi values. But then that multiset of phi values itself has more information than just its cardinality. And so so in other words, any invariant phi of Quandle colored knots defines a multiset valued enhancement invariant. And most of my research involves finding enhancements and studying their properties. So one thing with multisets, if the multiset gets big, it gets a little bit hard to work with. So for ease of use, we'll often encode it as a polynomial by summing over the multiset, taking some formal variable and taking the elements of the multiset, for instance, as exponents. Okay, so the first, historically speaking, the first enhancement was the CJKLS 2 cocycle invariant, and so we'll go ahead and review that. Also, I need it for this talk, for the construction I'll show you later. So let A be some abelian group. Doesn't have to be finite, but I'm generally going to be thinking of finite abelian groups here. So then the set of A linear combinations of ordered n tuples of elements of X form what's called the set of rack n chains. we can take the subgroup of those rack n chains where two neighboring entries are equal, and we'll call those n chains degenerate. And if we take the set of rack n chains and we mod out by the degenerate n chains, we get what's called the set of Quandle n chains. Okay. And then on the set of rack n chains, we have a map that's defined on the generators by sending the generator x1 through xn to the alternating sum of the result of taking out, so the alternating sum k going from 1 to n. In fact, with Quandles, you can start with k equals 2. But anyway, k equals 1 to n, minus 1 to the k of, we're going to throw out the kth guy to get an n minus 1 tuple. And then we're going to subtract from that the result of taking that kth guy that we threw out up here and using it to triangle all of the entries before the kth one. And then the ones after we'll just leave alone. Right. So this map turns out to be a boundary map. In fact, the condition for that to be a boundary map is precisely that the triangle operation is self-distributive. It also has the property that it sends degenerate chains to degenerate chains. So the set of degenerate chains forms a subcomplex. And so that means we can take a quotient. So we have our quotient complex. And so its homology is the Quandle homology with coefficients in A. And dualizing, we get cohomology, which is Quandle cohomology. So here is partly an example of how that works using Z, but then this is also a little bit more general. So, okay, so suppose you have a knot diagram with a Quandle coloring, right? So an element of the Hom set. Then you can look at each crossing, and if you draw the crossing with the strands pointed down, then if we take the two left-hand strands with the under crossing first, so this one is plus xy, positive crossing, this one is minus xy. Since we're modding out by degenerate chains, if you have a monochromatically colored crossing, that's going to contribute 0. So for instance, this Quandle coloring of the trefoil, here the Quandle that we're talking about is core of Z mod 3, also known as the Fox coloring Quandle. So each of these crossings is negative. So this one, we're going to have a minus 2, 1. This one, we're going to have a minus 3, 2. And this one, we're going to have a minus 1, 3. And so if we write the 6 generators here, remember, we're throwing out the degenerate ones. So we don't need 1, 1. So this one will be 1, 2. This one will be 1, 3, 2, 1, 2, 3, 3, 1, 3, 2. All right, so then we get this column vector with integer entries. Okay, so this is all building up to defining the original enhancement. So if you forget all about the Quandle cohomology stuff and just take a more kind of basic motivation question of, suppose we want to assign some value in A to each crossing in our Quandle colored knot diagram, and we want to assign those values such that the sum of those values over the whole diagram is unchanged by Reidemeister moves. Well, if you look at Reidemeister 3, what you need is that here you want your phi of xy plus phi of yz plus phi of x triangle yz should be the same as phi of xz plus phi of yz plus phi of x triangle zy triangle z. And it turns out that that is precisely the condition for phi to be a Quandle 2 cocycle. In fact, actually a rack 2 cocycle, but it works for, I mean, Quandle homology is quotient of rack homology. And so, so here we have only the Reidemeister 3 move, but if you consider Reidemeister 1, Reidemeister 1 moves are always going to correspond to degenerate chains, and we're modding out by those. So that gives us Reidemeister 1 invariance. And then just the coloring condition where we're adding, let me come back here, where we have a plus at this crossing and minus at this crossing. With stack those guys, you get the Rademeister 2 move. And so we get Rademeister 2 invariance from just the convention. So in other words, the upshot of this is that if you have a Quandle 2 cocycle and you evaluate that 2 cocycle at all of the crossings and sum those guys up, you get a number called, or an element of your coefficient abelian group called Boltzmann weight. And this is set up so that those Boltzmann weights are invariant under Rademeister moves. Okay. So now here there's a sort of a subtle point, which is that if we have our 2 cocycle with coefficients in A, then back here, we have our coefficients, our entries in our column vector representing the Hamset element have coefficients in Z. So if A happens to be Z, then this evaluation is just the usual inner product. But more generally, you can still evaluate a cocycle with elements in A, or with entries in A here when V, so this is phi is like a row vector, and V is like column vector, with these guys being in Z, because any abelian group is a Z module. So if you see like, 2 here times something over here, just think of that as the thing plus itself. Okay, hopefully that makes sense. Okay, and so then there's a lot more to the whole Quandle cohomology thing. For instance, it turns out the cohomologous cocycles define the same invariant. Anyway, when you repeat this procedure to get this A-valued invariant of X-colored diagrams over the whole Hamset, you get a multiset called the 2 cocycle invariant, or CJKLS invariant. That's Carter, Jalowski, Kamada, Langford, and Saito. Okay, so now we're almost done with the review part of the talk. If you have a map sigma from your Quandle X to itself that respects the triangle operation, so sigma of X triangle Y is sigma of X triangle sigma of Y, then we'll call that a Quandle endomorphism. And excuse me, the key insight from a paper of mine from back before the pandemic with a student was that if you apply a Quandle endomorphism to all of the colors in a Hamset element, here we get sigma of X, sigma of Y, and sigma of X triangle Y. But the fact that this is an endomorphism says that this sigma of X triangle Y is sigma of X triangle sigma of Y. So in other words, these new colors satisfy the coloring condition. And so what the endomorphism does is it gives you a map from one coloring to another. So in particular, if you make a vertex for each Hamset element, for each coloring, then an endomorphism gives you arrows between those vertices. So you get a directed graph, or what we like to call a quiver. And because this is all, so you can choose any set of endomorphisms. If you have, you choose the empty set of endomorphisms, then you just have the sort of naked Hamset, just the vertices with no arrows. But each choice of endomorphism gives you one arrow going out of each vertex and going into some other vertex, or possibly itself. So, for example, the Quandle coloring quiver for the trefoil knot with the fox coloring Quandle, and this choice of 2 of the 9 endomorphisms gives us a quiver that looks like this, right? So here, this one is a constant endomorphism setting everything to 1. You can see every vertex has an arrow going into this one, including itself. And then this 2, 3, 1 is a cycle, and so that's giving us these triangular cycles over here. Okay, and again, because all of the invariants for this quiver construction, sorry, all of the ingredients for this quiver construction are invariant under Reidemeister moves, then the quiver itself is automatically invariant under Reidemeister moves. And any information we can extract from it. So, okay, so that ends the review part. Now I'm going to tell you the new material. And so what we're going to do here is use Quandle cocycles to define a quiver representation. So in other words, an assignment of a vector space to each vertex and a linear transformation to each of the edges in the previously mentioned Quandle coloring quiver. So this is not one invariant, it's an infinite family of invariants. And there's a bunch of parameters, a bunch of choices that you make in order to do this construction. So I've tried to kind of organize these a little bit by making this data vector of these 5 things. And I've tried to make it easy to remember. So it spells out this pseudo word exacts, kind of sounds like exact, right? So you have X is the finite quandle, A is abelian group, could be infinite, but generally speaking, I'm going to think of this as a finite abelian group. C is a choice of set of Quandle 2 cocycles, specifically X cocycles in the second cohomology of X with coefficients in A. K is our coefficient ring for our vector space or module. And S is our set of Quandle endomorphisms. Okay. So then what we're going to do is, in the quiver, each vertex is a Hom set element. So it's representing a Quandle coloring of our knot diagram. And so to each vertex, we're going to assign a copy of K adjoin A. So this is the free K module on our abelian group A. So this is partly why I want A to be finite, because I would like to have finite dimensional modules here. So, but in other words, we just think of each of the elements of A as being a basis vector, and then we could take K-linear combinations of them. You can also think of this as the group ring if K is Z. Okay, and then we're going to associate a distinguished subspace, which I'll call V sub C of V. And this is just the subspace generated by the Boltzmann weights which are in A, right, for each of the phis in our set of cocycles. So if you choose just a single cocycle, then each of these distinguished subspaces will be one-dimensional. If you choose 2 cocycles, then they could be 1 or 2-dimensional because you could have, for a given vertex, you could have different Boltzmann weights, or they could be the same, and so forth. Okay, so then when you look at those endomorphisms, sigma, what sigma does is it's going to send a Boltzmann weight from one vertex to a Boltzmann weight from another vertex just by applying sigma, but keeping the Boltzmann weight the same. And so what this is doing is defining a linear transformation, sending one generator for a distinguished subspace here to a generator for a distinguished subspace over at the other end of the arrow. And so if we have multiple cocycles, then we just sum those guys up, and we get a linear transformation F sigma from the copy of K adjoin A at one vertex to copy of K adjoin A at the other vertex, that's mapping the distinguished subspaces to distinguished subspaces. All right, so let me show you how this looks with an example. If we take, in this example, X is going to be just the set 1, 2, 3 with this Quandle operation table. There are 5 Quandles with 3 elements, and they form 3 isomorphism classes. There's the Fox coloring Quandle, core of Z mod 3. There's the trivial Quandle on 3 elements, and then the other 3 are isomorphic to this one. So this is one choice of those. Okay, and so let's also let A be Z mod 3, but I want to make clear these are, even though these sets both have 3 elements, I'm not thinking of them as the same set. So I'm going to write these Z mod 3 elements as 0, 1, and 2, and I'm going to put little vector arrows over them to remind myself that these are meant to be basis vectors for K adjoin Z mod 3. Okay, and then if you compute the second cohomology of this Quandle X with coefficients in Z mod 3, what you'll find is that it's three-dimensional. These are the three linearly independent cocycles. But just to be clear, for defining this invariant, the cocycles that you choose do not have to be linearly independent. You can just choose any set of cocycles. Okay, I'm going to choose K to be Z, but it could be Q or R or C or whatever you want. Anyway, and so if you compute the endomorphism set for this Quandle, you'll find that it contains, for instance, 2 to 1. This is the map sending 1 to 2, 2 to 2, and 3 to 1. And I'm just choosing one endomorphism here in order to keep the picture relatively simple. Okay, and so then let's apply, this is our XACKS exacts vector. So let's apply this to the L4A1 link. That's the 4-2 torus link from before. And so when we do that, this is the resulting quiver that we get. So there's a total of, what is it? There's a total of 8, no, 9. There's a total of 9. You know, there's it's said that there are 3 kinds of mathematicians, right? Those who can count and those who can't. I told that joke at a talk once, and someone told me that I'm the 4th kind of mathematician. I don't know what that means. But anyway, there are 9 colorings, so 9 Homestead elements. So we get 9 copies of Z mod 3. But then when we evaluate our cocycles, you'll find that in some cases we get the distinguished subspace as the whole space, Z to the 3. I think, yeah, but in some other cases, like here we have Z to the 2, here we just have a single copy of Z. And then when you compute these F sigma linear transformations, we get the matrices that look like this. Right? And so this is our matrix, this is our quiver representation. Yeah, so with the same choice of exacts vector, but with a different knot or link, you'll get a different quiver representation. And so in my paper, I show some examples where the quivers are the same, but the representations are different. And so, you know, this somewhat elaborate construction is giving us a quiver representation valued knot or link invariant. Okay, so there's a lot of stuff that I plan to do with this in the future. This is mostly I wanted to kind of set out this construction and you know, start kind of thinking about what to do with this in the future. Why should we care about quiver representations? There's a lot of reasons. The most basic one is that these representations of the quiver give us new, you know, allow us to find some new invariants we can derive from them. But also there's a lot of important constructions in knot theory. So for instance, Cohomology, the Kovanov cube is a quiver representation, right? Historically speaking, studying quiver representations with knot theory has led to some very nice and powerful constructions. So as I said, there's a lot I'm planning to do with this in the future, but for now, what we'll do is content ourselves with 4 new infinite families of polynomial knot and link invariants. And so when you're defining new invariants, there's a trade-off between strength of invariant and usability. So for example, you know, you can kind of keep adding a bunch of new variables, keeping track of different things. And so, you know, you can define invariants that have like, say, you know, maybe, I don't know, 6 variable polynomial such that when you compute it for a knot diagram, you get some like, you know, huge paragraph of polynomial. And I feel like, you know, that kind of invariant can be very strong, but it can also be very like kind of difficult to use. Like if you're looking at 2 values and they're sort of obviously different links, then yeah, they're going to be different. But if they're just kind of, you know, you're looking at 2, like 20-line paragraph polynomials, it can be pretty difficult to tell whether they're the same. So I would, I'm just saying there's a trade-off between strength and usability. So for the polynomials that I'll tell you about here, I'm trying to preserve as much strength as possible, but still going for good usability. So the first thing we can do, easiest thing, is, okay, so we have our quiver representation. Let me come back here. And we want to turn this into some kind of polynomial. So one way we can do that for each matrix is to take the characteristic polynomial of the matrix. Characteristic polynomial doesn't contain all the information about the matrix, depending on your choice of base field and so forth, and depending on the matrix, but it retains a lot of the information about the linear transformation represented. So we can just take the characteristic polynomials of all those matrices and just add them up. And so I call that the edge characteristic polynomial. Another thing you can do is, so you can actually encode a matrix as a polynomial by just taking two variables, say x and y, with keeping track of the row number and column number, and then using the matrix entry as the coefficient and just sum those up. And so that's a two-variable polynomial that actually doesn't lose any information. It completely determines the matrix. I just call that the matrix polynomial. So if we sum those guys up over all the matrices, we'll call that the edge matrix polynomial. So these are two new families of polynomial knot invariants. What exactly their meaning is still quite mysterious, but I think it should be interesting to think about it. However, those two are kind of unsatisfying in a way because they're not really using the structure of the quiver. So in order to use the structure of the quiver, here are two new, so two more families of polynomial knot invariants. So what we can do is I want to find the set in each quiver. I want to find the set of maximal non-repeating paths, right? So the nature of these quivers, they all have the same out degree. It's just equal to the number of endomorphisms that we're using to construct the quiver. So in particular, leaves always will have in degree 0. And so what this means is that you're never going to have a path going from a leaf to a leaf. You're always going to have, so you can have paths that start with a leaf, but they're always going to end in a cycle. And in this one, it's sort of almost a tree, but if you look at a lot of these examples of quiver representations, there's usually a lot of cycles. In order to have finite length in these paths, I want to require that we don't repeat any edge in our path. And then I want to have maximal paths in the sense that it's not a subpath of any other path, right? So like when you have a cycle, you're going to be able to break that up into, if you have an n cycle, that will break up into n different maximal non-repeating paths and so forth. Okay, so anyway, you find the set of these maximal non-repeating paths in the quiver. Then what you can do is, because these matrices are all the same size, they're all square matrices, you can just multiply the product, multiply those matrices in order along the path. And so each path will have this matrix associated to it. So then we can take its characteristic polynomial and let's throw in another variable to keep track of the length of the path. And so we'll call that the path characteristic polynomial. And if we do that with the matrix encoding polynomial, then we'll call that the path matrix polynomial. Okay. So the polynomial values that we get for those four from the quiver in the earlier example look like this. Right, so these are, small enough polynomials that they're, easy to compare with other polynomials. So like I say, what is their geometric meaning? That I really don't know. It's completely mysterious to me at the moment, but I think it's something that would be interesting to find out. And so here's a table that shows the path characteristic and path matrix polynomials for a choice of exact vector. If you want the details, it's in my paper on arXiv. But I computed these for all of the prime classical links with up to 7 crossings. And so as you can see, I mean, these invariants are not, perfect. For instance, neither of the 2 polynomials for this particular choice of exacts vector distinguish L6A2 from L6A3, and there's a couple of other repeats in the table. But generally speaking, these invariants are pretty good. They are, distinguishing most of the links in the table. So really, the thing to keep in mind when you're looking at my examples is that, and this goes not just for this paper, but for all of my papers, like almost all of the examples in my work, these are toy examples. And what I mean by that is that they are small enough to be easily findable and computable by computer search, but don't make the mistake of thinking that these invariants are that the examples are illustrating the full power of these invariants, because these are just for small quandles, small choices of coefficient ring, and so forth. And so the real power of this infinite family of invariants is going to come from using larger biquandles and larger coefficient rings. But of course, to do that requires more computational power, or maybe improved computation methods. Okay, that's all I had to say. Thank you for listening.
Thank you very much for your very nice and inspiring talk.
Thank you.
And now I will stop the recording.